Welcome! In this series of videos, we will cover the design and implementation of a project, from initial design through coding and development to testing, using either the PowerBasic Windows or console compilers. Today we will look at running a star migration simulation using a graphics window. Today we are going to start a brand new project, and this one is going to be a simulation of empires expanding to the stars. It would be tempting to simulate an entire galaxy, but that would entail tracking a great deal of data. So what we're going to do in this application is track only 100 stars in a globular cluster. At the centre of the globular cluster, we will have a black hole, and the stars will orbit around this. So there will be star movement over time, and we can then map the expansion of each of the empires from star to star. To do all this, we're going to use a graphics window for the simulation display. This will allow the application to be coded in either the Windows or console compilers. We're going to be calling on some Windows API routines, namely the GDI Plus part of the Windows API. So I have included both the normal Win32 API library and a new library called GDI Plus Included Functions. To give us flexibility in the development of our simulation, I'm going to set up a number of constants. As our globular cluster is going to be in 3 dimensions, I'm setting up 3 constants for the x, y, and z coordinates. This will give us the maximum width of the simulation, the maximum height, and the maximum depth. I've also created a constant called map_edge. This is to ensure that no star appears too close to the edge of our simulation. Additionally, I plan on having reporting on the right-hand side of our graphics window. So we're having a width of the chart of 280 and a chart height of 200. And the width of our graphics reporter is going to be 300. We're going to set 1000 as the maximum number of years of our simulation, and the maximum number of stars is going to be 100. Having all this in constants will allow us to change these values should we need to do so easily during our development. We're also setting the mass of the black hole at the centre of the globular cluster to be 100,000 units, and the number of empires we're going to be tracking to be 4. So for each star we're going to have to store a certain amount of information, and we will create a user-defined type to allow us to store this easily. And then we will dimension an array which will be an array of this user-defined type. So here is our user-defined type. We have 3 values for the x, y, and z coordinates. We have a value for the mass of the star. And we have 3 values for the acceleration in x, y, and z directions. And also a velocity in each of these directions. This will allow us to calculate the position of the stars between each turn, as each star will be attracted by all other stars, plus the black hole at the centre of the globular cluster. Our final 3 values we're storing for each star are first of all colour. Initially, all the stars will be a shade of white, between 1 and 255. The more mass of the star, the nearer to pure white the star will be. The final 2 values are first of all for the owner of the star, if there is one. This will allow us to point this towards the empire. And finally, the status, which we'll use in later videos. Next, we're going to set up a number of global values. We have first of all a global array for the stars themselves, set up as an array of that user-defined type we have just specified. Next, we'll have a constant for gravitational force and a movement scalar. This will allow us to adjust the movement of all the stars globally. And next, a view distance. This is to allow us to adjust the view that the user will see on screen within the simulation. And finally, an array for the empires. This will allow us to set the colour of each empire. So within our PB main function, we're going to be setting up and displaying the graphics window. So we're going to be needing some local variables for this. So first of all, we will have a handle for the graphics window itself. And as we're going to be printing text to this window, we'll need a font. So we're having a handle for the font as well. And as we're going to have a simulation which is going to cover 1000 years, we're going to have something to store the year count number. And my plan is to take a snapshot of the simulation at the end of each year and save this to a file. So we're going to create a local variable to store this file name. So we have 3 global values we'll want to set in here, which we can always amend later. 1 for the gravity, 1 for the movement scalar, and 1 for the view distance. Next, we can dimension our array of stars. This is dimensioned using our star count constant, which will give us 100 stars set up with the user-defined type that we have previously defined. Next, we can dimension the empire's colors array, which we will populate shortly. Before we display our graphics window, we'll want to initialize each of these empires. So we're going to create a function called initializeEmpires to allow us to do that. We will create this function in a moment, but first we're going to set up our graphics window. If you haven't used graphics windows before, you'll find them quite straightforward. We first of all have to use the graphics window new command. This command instructs PowerBasic to create a new graphics window. We have a title at the top of the graphics window, in this case Star Migration, and we have a set of coordinates. It's to be positioned 50 by 50 at the top left-hand corner of the screen. The width of the graphics window is to be 1700 and the height to be 900. The handle of this graphics window will be populated into the hwin variable, and we can then use that hwin variable for other commands. First of all is to use the graphics attach command. This instructs PowerBasic that all graphics commands will be directed towards this window. Because we're using the redraw option, it means that PowerBasic will not draw anything to the graphics window that the user can see until we actually use the graphics redraw command. This makes drawing to the graphics window much more efficient. Next, we're going to set the graphics scale. This allows us to set the scale of the coordinate system within our window. So we're setting it to mapx, which is our constant, plus the graphics start width, and mapy as the height. Now that we have that set up, we can define the font we're going to be using when we print text to our window. We can do this quite easily by using the font new command. We're going to be using Courier new, and it's going to be 12 point. And the output from this command goes to populate the DW font variable. This is the handle of our font. And having defined this font, we can now set the font to be used in our graphics window by using the graphics set font command and the handle we have just populated. As this is going to be a star map, we'll want to have the background color as black, so we can clear the graphics window and fill it with the color black. And having done all that, we can then redraw the graphics screen so the user can get to see it. The commands that follow this will be the creation and running of our simulation, but we'll skip over that for the moment and actually handle what happens when the simulation ends. So when the simulation is ending, we'll change the colour to foreground green and black background. We'll set the position that we wish to print our text. We will print the text using the graphics print command, redraw it for the user, wait 5 seconds, and then close the window down. And our final step is to end the font. This frees up the memory used by PowerBasic when the font was created. So before we attempt to run our application, we're going to have to define this function. And if we do a test compile to make sure it compiles cleanly, and if we attempt to run our application. This creates our star migration graphics window on screen. It should now wait 5 seconds and then terminate the application. So we're now ready to start coding our simulation. So the first thing we'll need to do is to populate this function called initializeEmpires. Within this function, we want to set the color we're going to be using for the 4 empires we're going to be using. So this is going to be a very straightforward function, a simple for next loop, or 1 to the number of empires. As we know there are only going to be 4 empires, we're going to set the value in each of these to be yellow, violet, lawn green, and dodger blue. So this will give us the colour of each of the empires. once an empire has taken over a star, we will change the colour of the star to these colours. So if we go back once more to the PB main function, there's a few more bits of code we'll need to put in here. Before we redraw the graphics window to the user, we'll want to draw the boundary of the map. As it's the plan to have the left-hand side of the graphics window for displaying stars, the right-hand side is going to be for reporting, which we'll do in a future video. So we'll want to draw our map boundary. So we'll create a new function whose job it will be to perform that function. And we'll call that drawMapBoundary. This again is going to be a very straightforward function. We're using the graphics width command to set the width of the lines we're going to be drawing, and we're going to be using the graphics box command to draw a box on screen. And the colour we're going to be using is yellow. If we try running the application now, we will see there is our graphics window with a yellow box indicating where the stars are going to be. And on the right hand side, this is where the reporting is going to be. As there are going to be some random generated numbers within this application, we're going to have to seed the random number generator. So before we initialize the empires, let's turn that on. We can do this quite easily by using the randomize keyword and passing it a parameter which is the timer. So every time our application runs, it will be seeded with the current time. So now we can put in the section of code which is going to actually run our simulation. So our very first task is to initialize the stars. This will create our 100 stars, which will include the black hole at the center of the globular cluster. So let's create a function whose job it will be to initialize our stars. So we're going to be calling this new function initializeStars, and we'll set up some local variables. As we're going to be stepping through each of the stars, we'll set up a star counter and an X, Y, and Z coordinates for the position of each star. As we said earlier, the star at the very centre of our globular cluster is going to be a black hole. So let's place it first, and after that we'll handle each of the remaining stars. So I'm going to create a little function called placeBlackHole. And we'll create 3 local variables in here for the X, Y, and Z coordinates. And we're going to set these to be the very centre of the map, using the map X, Y, and Z constants. And we can now attempt to store the black hole position in our global array of stars. So the very first star will be element 1 within this array, and we're setting the X, Y, and Z values to the ones we have just calculated. And we're setting the mass to be the constant which we've set for the mass of the black hole, which is 100,000. Next, we want to place the black hole on the graphics map. We can do this using the graphics ellipse command, which in this case will draw a circle. So we're using its X and Y coordinates for the centre, and we're making it 5 units in size, and it's going to be a red circle with a red boundary. So if we try running the application now, we will see there is the red black hole at the centre of our simulation. So now that we've positioned our black hole, we now have to place the remainder of the stars. So we're going to use a for next loop, going from the second star to the maximum number of stars, which in this case is currently 100. And we're going to be setting the X, Y, and Z coordinates by using our randomize command, which will return a value between the map edge and the map X minus the map edge. Obviously, we don't want 2 stars occupying exactly the same position, so we'll need to do a test to make sure that the location we've just generated is actually empty. So we're going to create another function called emptyStarLocation to test to see whether this location is already occupied. We'll create that function in a moment, but we'll push on with this function to complete the work. If this star location function returns false, then we will regenerate the values for X, Y, and Z and retest. On the assumption that we find an empty location, we can then go ahead and populate our global array. And I'm using the prefix command here to save a little bit of typing. So we're going to be setting the element number within the stars array for X, Y, and Z values. And we're going to set the mass of the star between value of 50 and 255. This will allow us to set the colour of the star based on its mass. So now that we've completed that function, our global array of stars has now been populated. So our next step is to do a for next loop to step through each of our years of processing. So as this is a dynamic globular cluster, all the stars are going to move. So our first function we're going to create within this for next loop is something to move the stars themselves, based on how far they would move within a period of one processed year. So we're going to call a function called moveStars, passing it the parameter of the year count. In later videos, we're also going to be generating the movement of ships to move from one star to another, and a second function to update settlements on those stars' planets. So we will create those functions just as placeholders, and we will populate them in a later video. So the function we're now going to do is the moveStars function. This will work out our stars' new positions. So within this function, we're going to be doing a for next loop from the second star to the last star, as the black hole at the centre of our globular cluster will not be doing any moving. So we're going to be creating a local variable called S. This will be our star counter, and this will be a nested for next loop, as for each star we have to check its interaction with all the other stars, including the black hole. So this is going to look a little complicated, but we're going to be using some pointers here. Pointer for the first set of stars and a pointer for the second. So first of all, we will populate our pointer for the initial loop. This is done using the var pointer command, pointing at the element within our stars array. And our first task is to zero the accelerations of the star in all directions. And next we're going to do a nested for next loop, from the first star, which is the black hole, to all the other stars. However, the star is going to have no effect on itself, so if the S and T variables are exactly the same, we know it's pointing at its own star. So we will then iterate the second loop. And then we can populate our second pointer, the pointer to our inner loop, which is the element of the stars we are comparing against. Next, we have to work out the distance between the stars. And as we're using pointers, we can use the @ sign in front of the pointer variable to access that element within the global array. This saves you a fair bit of typing and makes the code look much tidier. Next, we're going to do a calculation to work out how much our star is affected by all the other stars, including the black hole. This will allow us to populate the acceleration x, y, and z values within our global array. And once we have checked all of the other stars for the first star, we can then work out our velocities in the x, y, and z directions. And having got these values, we can now populate the x, y, and z values within our global array. So we're adding to the x, y, and z values within the global array, and we're multiplying by our dx variable, which is our global constant, which we set up at the beginning of the application. Eventually, in a future video, we'll be changing the colour of the star to indicate which empire currently owns it. But in order to give us something to see on screen to simulate this, we're going to insert a little bit of code which we'll remove later. This will test to see if the owner of the star is currently 0, then we will take a very small chance of setting that value to the current owner, which is going to be a value between 1 and 4. So now that we've calculated the positions of all the stars for this particular turn, we now have to place the stars on the map so the user can see them. So we're going to create a new function at the end here called placeStars. This will place all our stars on the map from the array. So again, we're going to need some local variables for the x, y, and z coordinates, plus the colour and the star we're currently processing. So we're going to clear the graphics window of all content and then redraw it from scratch. So we're going to use the graphics clear command to ensure the graphics window is black. We'll set the colour to green foreground and black background. We'll print the year number at the top of the screen, multiplied by 10. And we're now going to redraw the map boundary. Next, we want to step through each of the stars within our array and display them on screen. So another for next loop. So we're going to work out for each star where the x and y coordinates physically on screen are going to appear. Next, we're going to differentiate between the black hole at the centre of the galaxy and all other stars. So as we did before for the black hole, we'll position it on screen using the coordinates stored in our array. And it will be coloured red. All other stars will either be a shade of white or coloured for their owner. So if we test who the owner is, if it's 0, then the star is not owned. And we're going to display the colour as it is held within the global stars array. Otherwise, we're going to point it towards the empires array. This will tell us the colour of the empire. Then we can use the graphics ellipse command to draw on screen a smaller circle for the star based on the colour calculated. And our final task is to use the graphics redraw command to display all of this to the user. So what we haven't done yet is to create the empty star location function. So we'll need to do that next before we can test the code we've put in. So this is going to be a simple for next loop, stepping through each of the elements within our global array of stars. If the past coordinates x, y and z match what's stored in the array, then this location is already occupied. So at that point we will exit the function immediately. And if we get to the end of the for next loop and we still haven't found a matching star at that location, we can return the value true to say the star location is currently empty. So if we try running our application now, we can see all our stars. And they're moving, they're orbiting round the black hole. We have some colour in the stars as these have been populated in our debug code. So there is our simulation ending. So what we've achieved today is we have created a globular cluster of 100 stars with a black hole at the centre. We have simulated a rotation of those stars round the black hole. And we've also coloured each star based either on its mass or the owner of the star. So this is a good beginning to our star migration simulation. In the next video, we will look at going further and pulling information out of the arrays and dumping this to disk, including a snapshot at the end of each simulated year of the current position, both in numbers in a CSV file and as an image taken from our graphics window. But that's it for today. Thank you for watching.